now the hydrogen bond is some kind of byproduct of some special type of covalent bond. So let me put it this way. Hydrogen bond itself is a kind of ionic interaction, okay? Between, it's not an ion. We cannot say the hydrogen bond is an ionic bond because no apparent like ions are involved, but it's an interaction due to the between two elements having like a certain partial charge. So with in that aspect, it's kind of an ionic interaction. And another thing is this hydrogen bond is a result of like when hydrogen was somehow fooled into having a covalent bond with some big I. So here we need to understand this particular condition of so-called polar covalent bond. So among these covalent bonds, there are two different types of covalent bond. One is non-polar covalent bond, and the other type is a polar covalent bond. And what's the difference? We will see in a minute. So if a hydrogen bond, the hydrogen was somehow having a covalent bond with a very big guy or a very greedy guy, should I say, any element having a high electronegativity. What's electronegativity? Is an indication or parameter of how greedy you are for the electron. So if you are really, really strong in trying to grab your desire to grab the electron, then you are very high in electronegativity. So the chances are that you get what you want is much higher. You desire so strongly, and then you will get that electron. That powerful guy usually said of having the high electron negativity. Examples of such element having high electron negativity includes like the top. Yeah, of course there is a top high. One of the highest, the element with the highest electron negativity is fluorine, F. But this fluorine, the occasion that we get to or we have to worry about this fluorine in the biology is very, very rare. Okay, we don't usually worry about the fluorine, but oxygen is a different animal, and oxygen is one of the the most or the strongest elements in terms of that electron negativity, which is followed by this nitrogen and also chlorine. And look at the position where you are, position of the carbon, which is very intermediate, and hydrogen is weak. It's just like that. So the higher the number you have the assigned to you as an element, and the higher the your electron negativity. It's like that. So when you have, for example, like between two oxygen is an element with a high electronegativity. However, both oxygens have such a strong electronegativity, those forces are cancelled to each other. So here is this oxygen gas doesn't have any kind of a polarity, so to speak. So this is an example of non-polar covalent bond. Here, among these four examples of covalent bond, hydrogen is, I mean, hydrogen itself is very low in electronegativity, so it doesn't count. And oxygen, I have just explained why even with this such a high value of electronegativity of an oxygen, it shouldn't be considered as any polar. And this methane, both carbon and hydrogen, the difference between their electronegativity is very minimal, so they don't generate any kind of the discomfort or conflict. So they are okay. So they are generally like overall non-polar molecule. This case is different because now, as you can imagine, oxygen is very strong in electronegativity and hydrogen is very weak in electronegativity. So in that case, the battle is always won by oxygen, and always oxygen will take the presumably supposedly shared electrons is usually consumed most of the time at the oxygen end. So for the hydrogen part, they have actually seldom occasion to be able to see their electron come to their side. So this kind of discrepancies create so-called polar covalent bond. So as you can see over here, both this model is represented by this so-called Bohr model, where you can see this each electron shells described in a two-dimensional way, and it's a 3D like a space filling model in both the cases. As you can see, at the end of the hydrogen, because usually the probability of electrons existing at that end is very, very low. That's why you have this this D, the Greek delta, lower capital delta stands for the partial charge. So partial charge is plus over here at the hydrogen end, and partial charge delta is negative at the other end, which is where the oxygen. So, because these shared electrons are mostly staying at that end. So as a consequence, this overall this water molecule is polar. That's why any kind of other ions are dissolved in the water. They quickly go into the solution because of this ionic interaction between this water's negative end and the cation, and water's positive end with the anion of the ion. So that's the reason why the water molecule become polar molecule due to. But what's more important over here is the fate of this hydrogen. So, like the hydrogen, once again, getting back to that definition of hydrogen bond, is that hydrogen bond always is formed when a hydrogen is involved in the involved in the polar covalent bond, which means whenever hydrogen is having the covalent bond with somebody having the high electronegativity. Usually, practically speaking, in biology, there's only two examples that we can think of. One is the oxygen, and the other one is nitrogen. Either one of these two, okay, whenever you have this, then you will, when hydrogen was involved in this, or hydrogen was involved with this covalent with the nitrogen, and you will always have this hydrogen bond will emerge. And then because this hydrogen will have this partially positive charge, and on the other hand, the other end will have this partially negatively charged. So this is what's happening. So then attraction will occur. So this hydrogen ion of having this partially positively charged end, and you will have another molecule nearby having this partially negatively charged end, and there will be some kind of a subtle interaction between positive and negative, and that is what we define as the hydrogen bond. Okay? So hydrogen bond can be formed between two water molecules in this way. Okay? And in general, like I said, it will be like whenever you have this hydrogen with oxygen having this covalent bond, or nitrogen, then you will have this partially charged area and at the end of this hydrogen. And whenever you can have this another electronegative element like oxygen or nitrogen, then you will have. So these are the two most common occasions where you can find this hydrogen bond coming. Okay. So once again, to sum up, hydrogen bond is a kind of byproduct of polar covalent bond where hydrogen is involved. Okay. Then that hydrogen end, which is partially positively charged, will have an attraction with any other molecules, the partially negatively charged part. So that's the kind of a way of summarizing and describing the characteristic of a hydrogen bond, right? So like here, as we have already seen, the hydrogen bonds are formed among different molecules of water, as you can see over here. But also another very important area where you can find the hydrogen bond is, for example, like in complex molecules like protein. And there will be a lot of different areas of partially charged, positively charged, like this, partially charged positively, like this, and also at the other end, the partially negatively charged, like this, and you will have this hydrogen bond established. And with that, actually you can have some very specific structure maintained. So if that is the complex, why shouldn't it's complex again? It's just that if this is a molecule of protein, for example, where all the proteins, their structure, fine detailed structure is extremely important, and this is one of the main like force to establish such detailed structure of a protein. So that's the hydrogens. So one very important utility or use is example of a hydrogen bond is that the water molecule, individual water molecules are like you have every directions, you have an opportunity of having this hydrogen bond one another. And that is actually the thing that defining the liquid characteristic of water. Water as a liquid is very flexible, so that it can be fit into any different shape. Like you can use any container. Why is that so? Because in the liquid water, this establishment, formation and the breakage of the hydrogen bonds are always happening randomly and instantly. So that's making overall the shape of water is so flexible like a liquid, so that you are looking at the bottle of water, then it can flow into anywhere. Another thing is, if you look at this, the ice, think of this ice. What's the difference between ice as a solid and water, liquid water? The number of hydrogen bonds formed is different, the main difference. Because in ice at a lower temperature, the molecular movement is more highly limited, because the molecules will move much slower. And then you don't have any flexibility and an energy of breaking all these hydrogen bonds constantly and here and there, and then re-establishing there. So you have a regular, so to speak, you have a regular social distancing, a greater social distancing, having each water molecule having one already fixed hydrogen bond with another partner. But then overall it will make the molecule very rigid compared with the liquid water. If you have in a given space, think about it, in a given space, if you had if you maintain more social distancing, like in the case of ice, as you can see over here, that's the ice. In the same area, you have fewer number of more water molecules occupied. But in the case of liquid water, due to this constant having and breaking the hydrogen bond, much more number of water can be accommodated in this small area, which is just absolute no in the era of a corona pandemic. So you should be ashamed of yourself, water, liquid. Then the problem is, then the density wise, this guy is less denser than this liquid water, so it will float on top of the water, which bears a great significance, because otherwise, like if the other way around, then every winter in this temperate climate, all the living creatures, the bottom of this river or pond, will be exterminated, and then new life form has to be re-established every spring. So every year new creation is required. But all these animals and plants can hold hang in there during the winter, and once the temperature becomes warmer, then they can re-expand, reactivate their lives. Is the very big difference between, and due to this particular physical nature of this water and ice. So this is not really significant, but to show the way they have this, the movement, they are simply vibrating on the ice status, whereas, hey, what's going on over here? What did I do? Yeah. So the vibration versus this the liquid having so much more flexibility is what the difference maker is. And so in addition to that, this the water having this particular hydrogen bond formation property also affect other the property of water together with this the characteristic of water being the polar in nature due to this polar covalent bond. So to name a few of them is like, so the cohesion and adhesion. Those two are actually due to this hydrogen bonding interaction and attraction to one another among this individual water molecule. Like cohesions are something that here in this figure, what you can see over here is in the example of cohesion. The water drop. Water drop has a little bit of a different shape in that, if you look at this, instead of having perfect round shape, you have usually the water drop in the form of a little bit of this sticky end. This is due to the characteristic of so-called cohesion, which means the water molecule themselves like try to attract one another, have a little bit stronger force, allowing the sticking to one another is the characteristic expressed as a cohesion. On the other hand, adhesion is like a wetting, surface wetting property. So due to this hydrogen bond formation ability, they can easily wet the surface if those surface is not really having any hydrophobic surface. So that's another, and we call it as an adhesion. And with this, both adhesion and cohesion, what's interesting is, I'm not sure if I can draw, this is very good, but a tree having, so like really very tall tree, like 10 meter or 20 meter and even beyond that, one might actually wonder how can it be possible that water in the soil can be climbed up into the very top of this, because it will be extremely difficult in terms of, I mean, against the gravity. How can it win out and then go up against the gravity force? Is actually mainly due to these two combination of these two forces, like cohesion and adhesion, plus some of the transpiration force to evaporate the water continuously. These three forces are combined together, enable the climbing of a water molecule up to very high in altitude. And another example of such peculiarity of water due to this hydrogen bond is here, as you can see, this so-called surface tension. Due to the force of hydrogen bond clinging together, some of the weak force, weak pressure outside of this system can be easily repelled, and with that, this whatever this the insect, I don't know exactly the name of this insect or whatever, let's call it cockroach. I know it's not a cockroach, but let's say hello cockroach. This cockroach can play Jesus Christ thanks to this surface tension. Okay. So hydrogen bond is a very weak chemical bond in strength once again, even much weaker than the ionic bond. However, it is extremely important, very important in maintaining all very finite structure, biologically important macromolecule structure. One example is just like in maintaining a DNA structure and also protein, as you can see in this example. DNA, if you already knew that DNA exists in the double helical structure, and those correct double helical structures are actually maintained by this hydrogen bond over here between these two strands. And also proteins, the delicate structures are all here and there. Some of the lot of different hydrogen bonds are helping tremendously about. And also when protein is trying to have an interaction, so here this area is the DNA, yes, and protein is trying to have like a fit in interaction over here. Yeah, although I have also shown an example of ionic bond between DNA and protein. That is not the only force allowing, enabling this specific DNA and protein interactions. Plus ionic, plus this hydrogen bond and some other miscellaneous weak bond all together as a very important determinant of any particular protein can play this specific interaction or not. Okay? So this individually, if you look at the individual basis, this hydrogen bond is extremely weak bond. However, in a mass, right, like because usually the hydrogen bond force is being exerted on in group, so in mass will generate very significant force, which is very difficult to overcome. Really. So it's something like you can easily compare such the hydrogen bond with the Velcro. Individual Velcro connection is very weak, but usually you apply this Velcro as a larger surface that there's a really reliable sticking force generated. So that's about. But before we jump into something else, once I have mentioned the hydrogen bond, especially in the water, I actually wanted to include this, but because of this space limitation on the lecture handout, when I was about to generate the lecture handout, so I couldn't. So here, taking advantage of this small the time and opportunity, allow me to go over another water related and also hydrogen related and also biologically important concept of acid and bases. Acid versus base or alkali. Generally, how do you know whether a certain substance is a strong acid or a strong alkali? It is determined by the ability of how strongly can you dump your hydrogen into the solution. So once you are in a solution, if you have a strong tendency of removing your hydrogen that once you have in the form of this hydrogen ion, okay, so you don't let the electron go, but simply proton. So this one is another name. Usually we recognize this as a proton. Why? Because in this status, all you have is, if the regular hydrogen, which doesn't have any neutron, lost one electron, so it doesn't have an electron because after becoming a positively charged ion, so all you have left in this is just one proton. That's why usually it is called a proton. So hydrogen ion and the proton are synonyms. Okay, sometimes you will see the proton referring as a proton, and some other occasions it's just referred as the hydrogen ion. It's the same thing together. So anyway, if any strong acid will be able to easily, quickly generate hydrogen ion in the solution. In other words, if a strong acid present in dissolved in the water, then the hydrogen ion concentration the proton concentration of the solution will go up as the action of the strong acid. That's the definition of a strong acid. And then the opposite is true in the case of base or alkali. So how quickly and readily you can scavenge those dumped hydrogen in the solution is the parameter describing how strong base you are. So if you're a strong, so one such a very strong example of a base would be OH, hydroxyl group, because if you have this OH, then this hydrogen ion will easily attach to this and then restoring its status as a water. So this balance of power between strong acid and strong alkali or base will now then have this neutralizing effect. So anyway, that's the definition and distinction between acid and base. Usually the acidity or like the degree of a base or alkali is described as some particular value we recognize as called pH. pH is the parameter describing particular concentration of the hydrogen. So in biology and chemistry, the concentration is usually expressed in this square parenthesis. So this hydrogen ion concentration is described in the negative log. If you didn't know what the log is, then for me it would be difficult. But hopefully you roughly, vaguely know what the log is. Then if you put the log of the hydrogen ion concentration, why did you do that? It's because this concentration of the hydrogen ion at the neutral, like a pure water as was set as a standard, the pure waters, the concentration of the free hydrogen ion, because pure water is just a neutral, doesn't really contain too much of hydrogen ion in the solution. And then it will be something like 10 to the minus 7th, like 0.1 mole. Okay, so that concentration. So if you put that in here logarithm, then it will become, because of this value, it will become automatically a negative value to compensate such intrinsic negativity in value. That's why you define the pH as starting with the negative value. Then overall the pH value will become positive. Okay, so having said that, then by definition the pH of pure water will become what? 7. That's why pH 7 is used to indicate the neutrality. So over here, if you have a higher concentration of hydrogen ion, then this value, this negative value will drop, right? So in other words, the pH value will be lower than 7. So that's why you have here, the stronger you go toward the acidic range, the pH value will become like 1 or 2, 3. All these are the strong acid. In other words, another thing that you want to remind yourself is the only difference between the pH 1 and substance like pH 2. Hey, there is only one digit the difference. However, in reality, it is a 10-fold the difference in real concentration. So like pH 5 and pH 7, there are 100-fold difference in terms of this acidity, the hydrogen ion concentration. So the coffee pH having the pH 5 is a fairly acidic substance. Although I cannot avoid coffee, so no matter what, whether it's like pH 4 or even pH 3, I have to have a coffee. So it doesn't affect my decision making regarding coffee. But anyway, and then if you go to the other spectrums, like if you go toward the strong base line, this pH value will just keep increasing like that. So you can have a kind of a rough idea about what are all those the materials, including food, that you are usually familiar with in your life, has actually some of the characteristic of base or acid. And this acid base, in terms of like trying to view in terms of hydrogen ion concentration, I will revisit this concept of being acidic attached with the hydrogen ion concentration later, in later chapter, when we get to deal with some other cellular component aspect and some other biochemistry area. So that's why I felt compelled to go over this acid and base things. Okay, so with that, we can fold the chapter of the hydrogen bond. And it's not a big chapter.